So I was asked back in November to create a 3D printing class for a DITRA program that was going to happen in Albuquerque. And as everybody knows, with COVID-19, pretty much all live classes in this state and most other states were put to a stop. And DITRA decided not to do that program, but some of the people I interfaced with at Oak Ridge Associated University, they asked me to put together a program instead for remote teaching of 3D printing for some students elsewhere in the country with another one of the sponsors they deal with, which is the Appalachian Regional Commission. And so we scrambled very quickly to put a class together. We really didn't know it was going to happen for sure until the end of May. So the Oak Ridge Associated University was willing to bring equipment over to the makerspace here in Los Alamos to let us do this kind of class. We wanted to do a class that wasn't just 3D printing. This program traditionally has a big science component, and so while it's great to teach 3D printing to students, we wanted to get some science out of it too. And we came up with the idea of strength testing parts. The original inspiration was the popsicle bridges that people would make for architecture and engineering classes. And instead of popsicle bridges, we're going to have 3D printed bridges. So all the students, and we had 8 students in this particular program, got a 3D printer like this one. And we all assembled the printers together, sometimes with some hiccups. And we learned how to do 3D printing, all the software that is required for that process. And we learned some CAD. And they actually designed bridges. And ultimately, those bridges are going to be strength tested in a strength tester that we built. So the students all printed things and actually shipped them to us overnight in FedEx boxes, and we tested them here. So they shipped prints to us, and we also printed some designs they made. And we ended up strength testing about 100 different pieces using our strength testing setup. And the students were able to analyze that data and actually come up with some conclusions based on the data. So we were able to actually do essentially a science lab in an all-remote mode. It's the first time we've done anything like this, and we were really pleased with the results. The students got a lot out of this, and so I'm hoping that we will be able to do more remote classes like this in the future for students who can't come somewhere to a school and do this kind of summer school. All of the students received a 3D printer like this one. It was a box of parts when they got it, and we spent the first day of the class assembling this printer. And as you can see, it works just fine, and really printers that anybody can afford now are easy to get. And this took about 4 hours for everybody to assemble. So with those printers, all the students printed some standard parts. And the goal of this was to actually strength test the same design printed on multiple printers. We were able to get some statistics out of this. So they printed 2 cylinders and 3 bridges. And they were all designed slightly different ways. And we strength tested them. And you can see they had patterns for braking that were consistent. So in this bottom row, the bridges tended to shear in the middle, or shear vertically. In the middle row, they tended to break in a more kind of diagonal fashion. And in the last row, kind of the same thing. And we found that the printing orientation really was important for how strong these bridges were. With the cylinders, we tried 2 different methods of printing these, and they actually really saw no significant difference. And they were able to take all of the data from these crushes and do some analysis to actually determine, is there a significant difference in how you do the printing in terms of the strength of the part. And this was a really cool thing that the sponsor paid for, to have overnight boxes for the students. So at the end of the first week, they were able to mail all these to us, and we were able to get them crushed and have the students do the analysis all within 1 week of receiving the parts. So that part of the program really worked great, and I'm hoping it's a model for some future remote laboratory kind of classes. So this is the hydraulic press setup we use to strength test prints. And this device here is called a load cell. It was actually in line with the piston, and it would measure the force being exerted on the part as we crushed. And all of the students' bridges were tested this way. Now today we've got something a little different to crush, but I will demonstrate how this worked. And it is no trouble at all to crush most things with this press. So that's not too interesting. But we can easily change parts. This is something that's going to be a little more fun. And this is a little bit closer to what the students actually used. The worst part of the whole process was operating the pump to get the piston in place. We can only afford so much in terms of hydraulic presses. So this one's a manual. But we would be able to strength test the parts this way, and when that happens, you're done. So one of the cool things you can do with this setup is you don't just have to do science, you can occasionally have some fun too. And we have a lot of 3D prints lying around from the years at the Makerspace. So this is a skull. I'm going to see what happens when we crush it. Wah! That's probably enough. This is how we strength test bridges. Normally, the load cell would be under the bridge, or under the test stand, which is this aluminum stand. But we'll leave that out today. And we have a 3D print. This is re-breaking a bridge, actually. And we're going to see how strong it is when we crush it. And what you're about to see is the reason why we built this big enclosure. Sometimes when this breaks, it's dramatic. It will shoot parts flying. So, here we go. And that is why I built an enclosure. Now, this was the bridge that's the weakest design. And you can see the way it broke, just like that. It sheared in between layers. If we had put one of the stronger bridges in, that would have been a lot more dramatic.
Hi, my name is Conrad Farnsworth. I am a board member at the Makerspace. Jacob reached out to me a few weeks ago asking if I could lend a hand for this class, and naturally I recruited the two smartest people I know in my life, somebody who's good at squishing and breaking things and somebody who's good at 3D printing the things that we were going to later squish and break. My role in this class was to get the broadcasting setup going where we could watch the pressure on the load cell in real time with the actual crushing data, the video data that we were getting. And thanks to Amanda for setting up the load cell. It was pretty challenging.
Yeah, I mean, there's a lot of different features that you have to set up when you're setting up a load cell, so it's complicated, but good.
But good. And Remington, you know, was it any difficult to get the 3D printer going, or is it pretty out of the box?
We had pretty good kits this year, which is nice. Things have come a long ways in the last 5 years or so. So we get the students spun up pretty quickly, printing stuff, and everybody actually had some successful prints.
How difficult was it to teach the children how to slice?
Not too difficult. The software has also gotten better along with the hardware side of things. So yeah, my main focus was getting the students spun up on their slicing software for taking our 3D files and turning them into the G-code necessary to actually run on our printers. So that was my main thrust for the project, giving a little bit of a lecture on that. It was really nice, getting some students excited about 3D printing.
Amanda, were you excited about, or were you happy with the quality of the load cell that you brought in?
Yeah, no, it was good. So my role was getting that load cell all set up and running with Conrad's help, since he's the electrical. Well, I guess Remington is too. So more help with electrical, as I'm a mechanical engineer. And then I gave a couple lectures to the kids on the art of squishing things and mechanical design. So tips on making their bridges that they were designing stronger. And then they sent us the G-code for those bridges, and then we later crushed those in the week, and they had a chance to revamp their design, and so then see if they improved how strong they were. And most of them did improve quite a lot. Actually, it was great.
Were you surprised with the strength of the bridges?
A couple of them. The load cell was rated to 2 tons, and one of the bridges went to exactly that. And if you go above that on a load cell, it'll break. So we were quite nervous that it was going to smash the load cell. So the bridge was stronger than our setup, which was good.
Excellent. My, I guess my contribution, lecture-wise, was more of a kind of a more of a hacking sort of way of rebuilding parts that were either broken or you only have pictures of. And I was able to teach the kids how to take an image and then turn it into an actual 3D model with complex geometries around the exterior of the model and 3D print it.